Well, hello everyone. Welcome back to your third lecture of BSc 1005, better known as Biological Principles for Non-Majors. Again, this is an introductory course to biology, and I hope you all have enjoyed your first two lectures so far. Obviously, with everything going on with COVID, I would much rather be giving these to you in person, but it's just kind of how we have to deal with things, with especially having a class that would normally be really, really big like this one. So I hope you're at least getting some stuff out of this. And I hope y'all are staying safe. Um, so, without getting too sidetracked here, let's go ahead and just kind of do a couple quick reminders. So, just a reminder that your syllabus quiz is due Friday, August 28th. Remember that it is really, 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 really important that you do this. It's the only way you're going to get your financial aid for the semester. The state of Florida actually requires that we check and make sure y'all are doing or actually attending the class before they'll give you the money. So please make sure you are doing this. It is really, really important. And make sure you'll probably have lots of these quizzes. Please make sure you're taking the quiz for the right class. So you're probably going to have to do multiple of these. Make sure you're doing all of them. Second, remember that your week one quiz is due by next Monday, August 31st. It will close at exactly 11:59 on Sunday night. So please, please, please make sure that you are doing these. Remember that you are going to have 14 of them over the course of the semester, and only 12 of them count. So if you do miss one or two, it's probably not the end of the world. But please make sure you are doing them. It's really, really important. So again, while we're kind of talking about just how to do well in this class, because I realize that most of y'all are probably in your first semester or two of college, some just kind of important study tips that I think might be really useful, especially in context of having this kind of odd class where y'all are watching lectures and all that kind of fun stuff on the internet. First, most important thing is make sure y'all are getting plenty of sleep. Not only will it help you improve focus and improve your memory, but it's just really good for your mental health and your physical health. I remember earlier this summer, due to everything going on with coronavirus, I actually went nocturnal for a good portion of the summer, where I was getting up at 2 or 3 o'clock in the afternoon and waking up at like 7 or 8 o'clock or going to bed at like 7 or 8 o'clock in the morning. And that really wasn't pleasant. So, it throws off your sleep schedule. It throws off your food schedule. You end up gaining a ton of weight. Yeah, it's not fun. So please make sure you all are taking care of yourselves. It is really, really important during this time of everything going on. So please try to do your best if you can. The other thing that I really, really recommend is make a schedule and stick to it. This is going to seem really tedious at first, but it's likely to give you a lot more space in your day. Specifically, it's going to give you a lot more flexibility in like how you're going to get things done, and you're going to have a good allotment for what all you need to get done too. So, plan for, say, to watch all your classes between 9 to 12, obviously take some breaks and all that kind of fun stuff. And then spend the rest of the afternoon studying and doing all that kind of stuff that you need to do, maybe taking your quizzes or your tests, whatever. And make sure you're allotting time to, not only just watch the lectures and take notes while you're in lecture, but then take the time to transcribe those and do what you can to make sure you're really retaining this information. Because obviously it's going to be stressful no matter what with everything going on. So just kind of hang on there. So I do want to do a little bit of a review of the previous lecture. So for those of y'all that are breaking these up, across a couple days, it probably will feel not super fresh, but it'll at least refresh your memory. But for those of y'all that just watched the previous lecture, you can probably skip over the next minute or so. But we're going to go back through the branches of life and kind of break those down a little bit better than we did the last time. So remember that the tree of life is broken up into three main branches. We call these domains. And specifically, there's kind of two breakdowns of the domains. You have the prokaryotes and the eukaryotes. And species are broadly categorized into one of these three domains based off of the differences that we see. That graph that you see below on the left is called a phylogenetic tree, which shows how close species / kingdoms or domains or whatever are related to each other. And the points where those things break off are called nodes. They show the most common ancestor. So say, for instance, you're looking at animals and fungi in domain Eukarya. That point where they break off is called a node, and that shows the most recent common ancestor between animals and fungi. And it shows that animals and fungi are actually more closely related than, say, animals and plants or fungi and plants, even though, which is kind of counterintuitive, because if you think about a fungus, you often more think it's closely related to a plant just based off of looks and all that kind of fun stuff, even though they're pretty different. So again, remember these domains are divided into kingdoms, and all three domains include at least one, if not many, multiple kingdoms. They represent thousands to millions of different species. Just a single kingdom of animals contains millions of species, plants and fungi just as well. And a lot of that too is sometimes we just haven't discovered everything. So you never know what all cool stuff might be out there. So do keep in mind that there's millions of species represented in each one of these kingdoms. So these are pretty broad branches, and it makes it kind of difficult to discern exactly where things broke off. Now, the relationships between the prokaryotes and the eukaryotes isn't always really well established, because keep in mind that there's a lot of very different branches that have broken off over the thousands and millions and billions of years of Earth's existence. And so some things that may link this one random protist to the first eukaryote back to the prokaryote that it came from may not easily be readily available. So it is kind of difficult to necessarily discern all these relationships, especially at this big broad scale, but it's still interesting nonetheless. So again, remember that the prokaryotes which are two domains, bacteria and archaea. They're both prokaryotic and unicellular. So that means that they don't have nucleus, they don't have any other cell compartments, so no mitochondria, no chloroplasts, nothing like that. And that gives them a lot of abilities that, they can handle some crazy situations. And that's where you get the crazy extremophiles that occur in archaea, where they can live in, waters at 140 degrees Fahrenheit, or, the bottom of the ocean in the Antarctic, or in these crazy sulfur lakes or salt flats. There's some really weird places that you can find some of these critters. Now, remember that these two domains do differ, but we're going to wait to explore those differences until a little bit later on. And it usually is related to cell wall composition, whether or not a bacteria can form spores, whereas archaea don't. There's a couple other little things that we'll get into, but we're going to hold off on that for now. Then we get into eukarya, which are the most diverse group, probably, with protists being the most diverse group of eukaryotes. There's multiple kingdoms within Protista. They're either unicellular or multicellular, and they can either be autotroph, which means they're producing their own food. Remember, producers, autotroph, self-feeding, or heterotroph, other feeding, which means that they consume other things, and that can either be through a variety of different methods. And these organisms in the domain eukarya have very, very complex cells with nuclei. So, there's protists that are closely related to plants that have chloroplasts, things like algae and stuff like that, whereas others are more almost animal-like, like the amoeba, that have been hypothesized to ultimately have become animals at some point or another through evolution. So just remember that these protistans are a very, very diverse group. And it's sort of a dump kingdom in which all this organisms that have, a nucleated cell, but aren't animals, plants, or fungi get kind of thrown into. So it's a very polyphyletic group, which means there's a lot of different nodes branching off in very different places. Then we get to Kingdom Animalia. It's one that we probably know the most well. This is a familiar group of eukaryotes, including things like fish, frogs, and humans. They're all multicellular. They're all heterotrophs, and primarily obtained through ingestion. Fungi are nature's decomposers. They're mostly multicellular. There are some single cellular ones, including some really nasty pathogens that specialize on frog skin called the chytrid fungus, which is really nasty. It's actually the worst pathogen known to science. And they're heterotrophs, which they obtain their energy through external digestion. So instead of consuming something, they're pulling it out of the environment and externally. So it's a little bit different. But again, all of these things kind of can have some of their own caveats as well. And finally, we get to Kingdom Plantae. These are multicellular organisms that produce their own energy primarily through sunlight and they're primarily autotrophs. However, that's not entirely the case. There are parasitic plants as well as carnivorous plants. So again, there are caveats to that whole autotroph thing. So with that little bit of review done, remember that we kind of talked about how there's a structure of how we look at biology, which is using scientific inquiry to study life and looking at how life has these 5 properties and it can be classified into these 3 domains, and that scientific inquiry relies on hypothesis and experiments. All this stuff is going to be really important, and expect it to be pretty important to your next quiz or two. So make sure you're getting really comfortable with a lot of this information. If you can't quickly figure out what's on this graph and move on and be able to do the quiz, you're probably in trouble. All right. So let's start moving into our next segment here. We talked about how life is kind of consisting of these units called cells, which are composed of all these different molecules. And in order for cells to carry out all these things, they have to be able to, one, obtain new molecules to be able to grow and reproduce and all that kind of fun stuff. And as well as just continue to exist, because they're going to have to pump certain things out of their cells or pump certain things into their cells to maintain homeostasis. And so that and it can be everything from they need these molecules to create proteins or carbohydrates and use ATP during respiration or photosynthesis in plants, all these kind of stuff. It's really, really important. But ultimately, what this means is we do need to take a step back and review some chemistry, which I know everybody's favorite subject. Chemistry is definitely not mine, but chemistry is really, really important when it comes to cells. Especially when you think about things like the molecules that are consisting of atoms, which comprise DNA and ultimately help create proteins and are the composition of proteins, the carbohydrates that get used for, all these various things. It's really important to understand how all of this stuff is interrelated. And in order to do that, we really need to understand the chemistry behind it. So we're going to dig a little bit into the chemistry section here. But first, I want to kind of just do a very basic broad statement in that, what is matter? Obviously, life matters. This dog, the water that you see there, the air are all form of matter. In this case, matter is any material that takes up space. So everything in that picture, every form of matter in the universe consists of chemical elements. So in the water, you have hydrogen and oxygen. In the air, you have nitrogen, carbon, oxygen, and hydrogen. And so many elements are fundamental types of matter. So in order to understand matter, we really need to understand those elements, things that we have already kind of mentioned a little bit. So an element is a substance that cannot be broken down by any chemical means into any other substance. It's probably the most pure way to put things. In other words, this is the most base thing that something can be. It cannot be broken apart anymore. And if it is broken apart, you get massive releases in energy that are the staples of nuclear fission. So probably best to not keep dividing things. There's that. So here you can actually see the periodic table. This lists all the known elements in the universe that we currently know. And some of these have only been hypothesized and created in labs. Other ones are fairly common around all of us right now. You're breathing in oxygen right now. You're also breathing in some nitrogen, maybe a little bit of hydrogen, and all that kind of fun stuff too. And whether they be in the form of air, water, all of that kind of fun stuff. So the periodic table that you're seeing below there is an abbreviated periodic table that only shows some of the more important elements in life. So in this case, it's broken up into bulk and trace elements. Bulk elements are going to be the elements that are very, 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 very common. So in this case, hydrogen, sodium, which is Na, magnesium, potassium, calcium, carbon, nitrogen, oxygen. And then these trace elements are going to be elements that aren't super found often. So copper, cobalt, nickel, zinc, chromium, a lot of those kinds of things. Now, just because it's a trace element doesn't mean that it's not required for even your own body. I believe there's a certain amount of copper your body needs to be able to properly function. So kind of a random side, my dad is on dialysis. And so as a part of where they pull the blood out and filter it and put it back into his body, it can often strip a little bit extra of the metals and that sort of stuff. So he has to actually be taking constant copper supplements, because without that, he wouldn't have enough copper in his body and your nerve cells don't fire properly. So even though they're called trace elements, it doesn't necessarily mean that they're not super, super useful. So about 25 elements are essential to life, all of which are highlighted. The bulk elements are required in large amounts because they're making up the majority of the living cell. So about 96% of the human body is made up of 4 elements, and that's oxygen, carbon, hydrogen, and nitrogen. Those are not gases. The elements are bonded with each other in varying combinations and form various molecules. For example, oxygen in particular can be found in water, sugars, fats, as well as the same can be said for hydrogen. And again, like my copper example, trace elements are important too. Despite what your proportion might suggest, our thyroid gland actually requires trace elements of iodine, and if there's not enough iodine in your diet, they become bigger and forming a growth called a goiter in the neck. Blood cells require trace elements of iron to carry oxygen to the body's tissues, and an iron-poor diet causes anemia. Too much is toxic. So you have to be kind of careful with some supplements. You don't want to just be willy-nilly just eating a lot of supplements, and you can totally throw yourself off. Now, usually your body kind of counteracts this, but obviously there's only a point where that can go so far. So this chart or periodic table organizes the elements. Each box gives us a couple different things. It tells us the atomic number, the element's full name, the element's symbol, and the atomic weight. All of these are really, really important. And it's okay if it doesn't make sense quite yet, because we're going to dig a little bit more into this as we go on. So kind of bear with me here for a minute. So remember that an atom is the smallest piece of an element that retains the characteristics of that element. And an atom is composed of 3 smaller particles: protons, which are positively charged, neutrons, which have a neutral charge, and electrons, which are negatively charged. Electrons surround the atomic nucleus, which contains both the protons and the neutrons, and they're very small and move very, very fast. Protons and neutrons are close together in the atomic nucleus, which is at the center of the atom. So compared to neutrons and protons, electrons are basically weightless. So when you're calculating the mass of an atom, only the mass of the protons and neutrons is really kind of taken into consideration. And for simplicity, electrons are kind of pictured much closer to the nucleus than they really are. They often can form these really complex ring structures that can be very, very difficult to model easily. And especially if you're taking chemistry, these ring structures will be the bane of your existence. So if the nucleus of a hydrogen atom was the size of a small marble, the diameter of the whole atom itself, which includes that electron field, will be longer than a football field. That electron cloud occupies so much of that volume. And if most of the volume is this cloud, all this empty space, it's basically because everything is moving together so quickly and spinning, it allows us to feel like there's something still there. Think about it as like if you're looking at a spinning fan. These electrons and protons are moving around so quickly that it basically looks like, if you're staring at a fan, how the fan just looks like a single circular blade instead of all the individual fan blades. So it's kind of a similar concept. So subatomic particles, again, are electrically charged. So you have electrons, which are negatively charged, neutrons, which are don't really have much of a charge to them at all, and protons, which are positively charged. And the number of protons present in that cell is what gives it, in that atom is what gives it its atomic number. So for instance, hydrogen, which is atomic number 1, has 1 proton. Now, this is going to get a little bit more complex because we now need to account for neutrons as well. So here's kind of a quick question. How many protons are in the N atom? So N for nitrogen. In this case, we'd look it up. We'd see that N has 7, an atomic number of 7, which tells us that there's 7 protons and probably 7 electrons as well. If we look at oxygen, which has an atomic number of 8, it's going to have 8 protons. Helium, 2. You see how this goes on. However, you then have to ask how many neutrons are in something, because obviously it's not just protons that are making up that nucleus of this atom. And with that, that's how we're going to get to the atomic mass or the atomic weight. So for instance, and that's why it's kind of important to consider these sorts of things. So ions are charged atoms. Ions are formed when an atom either gains or loses an electron. So for instance, the hydrogen ion, which is H+, is positively charged because it's lost its only electron and is left with just 1 proton. So in this case, you have a neutral, on your left there, you have a neutral hydrogen atom, which has both a proton and an electron. It doesn't have any sort of charge because there's the electrons outweighing the positive charge of the proton. But when we lose that electron, it then becomes a hydrogen ion, which is positively charged. So this can get complicated really quickly. And keep in mind, too, that they can also be negatively charged as well. So for instance, chlorine, Cl, you actually would lose an electron, which makes it drop back a little bit. So we've kind of already hinted at this a little bit. Protons and neutrons together are combined make the atomic mass of something. So an atom's mass number is the total number of protons and neutrons in its atomic nucleus. And again, this is going to be something they're going to give you on most periodic tables. So for instance, if we look at carbon, carbon has a atomic number of 6, which means that it has 6 protons. However, its mass, atomic mass or atomic weight, is a little bit over 12, which means that it has 6 protons and 6 neutrons in its base form. Now, keep in mind that this can change a little bit as we go into different things, and we'll get into some of those in a second. So that brings us to what we call isotopes. Now, isotopes are different forms of the same element, and the way that they actually differ is based off of the number of neutrons that they have. So if, say, for instance, carbon is probably a really good example. If you've ever heard of the term carbon-14 dating, what is happening is that's a regular carbon, or you have these carbon isotopes where it has 6 protons, and instead of 6 neutrons like a normal carbon atom, it'll have 8 neutrons. So then it has an atomic mass of 14. Now over time, which it's roughly about 10,000 years, those atoms will degrade and those neutrons will go shooting off into space, and it'll ultimately become carbon-12. And so by looking at the ratio between carbon-14 and carbon-12, we can actually date something and see how old it is. So it's kind of neat. It only works till about, I think, 100,000 years old, maybe 1,000,000 years old. It just kind of depends. But still, that's how these isotopes, at least in a biology context, can be really, really useful. So just remember that an isotope is any of those different forms of an element. So here you've got examples of carbon-13 and carbon-14, where carbon-13 has 7 neutrons and carbon-14 has 8 neutrons, whereas the base original carbon atom usually only has 6. So definitely can get kind of complicated. And this really isn't something we're going to focus on too much, but it will kind of help you guys along the road, especially if you're taking any chemistry. So again, remember that these isotopes can actually decay over time. So a carbon-14 atom is not going to always stay a carbon-14 atom. It just kind of depends. So remember that this atomic weight is the average mass. So carbon's atomic weight is close to 12, even though some carbon isotopes have an atomic mass of 13 or 14. This is because about 99% of all carbon isotopes have an atomic mass of 12, and the other, 1% or so are made up of carbon 13 and carbon 14. So it's really important to remember that these atomic weights are not integers. So they're not whole numbers. It's not just 14 or 12. It is 14.0067. And that reflects the existence of all these isotopes that we talked about earlier. All right, so I'm going to have a little bit of a practice question coming up. So the atomic weight of nitrogen is very near 14, indicating that most nitrogen atoms have a mass of 14. How many neutrons does the average nitrogen atom have? So in this case, you're going to look at that box, see that it's got an atomic number of 7, an atomic mass of 14, and hopefully you'll all be able to figure this out. I'll give you about 10 seconds to think on your own. All right, so what was your best guess? So given that we're asking what the atomic weight, given that we know the atomic weight and the atomic number for nitrogen, and we want to know how many neutrons an average nitrogen atom has, we'd go with B, 7. And the reason for that is 14 minus 7 is 7. Pretty straightforward. And I hope you all feel really comfortable with this because it is something that's going to probably come up a decent bit. So chemical bonds link atoms together. So atoms are organized into molecules, which are 2 or more chemically joined atoms. Now, for example, if you look at these water molecules, you have 2 hydrogen atoms and an oxygen atom. And these compounds are molecules of 2 or more elements. So during the previous lecture on organization of life, we saw that atoms are organized into molecules, and these atoms don't necessarily organize into molecules randomly. There have to be some sort of conditions for these chemical bonds to be formed, and we will look for these conditions in a minute. So let's go ahead and start with chemical bonding. So there's a number and distribution of electrons around an atom determine whether and how the atom will react with other atoms. And it's all based off of exactly how these electrons fit into that electron cloud that we were talking about earlier. So say, for instance, if you look at that hydrogen atom, you see that it really only can have 1 more electron that it can gain, whereas carbon can pull in an electron on either side, nitrogen can pull in 2 or 3 electrons, that sort of stuff. So these energy shells or orbitals contain the atom's electrons. These shells exist at various distances from the atom's nucleus, and the shell farthest from the nucleus is the one that's most important for bonding. And that's because that's usually where those bonds are the weakest between the protons and the neutrons. So the electronic charges that are holding that atom together, they're weakest on that most outer band. And you can really see that these atoms have different amounts of energy shells. With the first energy shell, the one that's closest to the nucleus can usually only hold about 2 electrons, and all others hold about 8. So atoms are stablest when their outer shell has no vacancies. So unpaired electrons form bonds with other atoms, and vacancies make those atoms less stable and more likely to bond with other atoms. Except for the first one, each energy shell can hold 8 electrons. And we have atoms from hydrogen, carbon, nitrogen, oxygen, neon, phosphorus. Which one is the most stablest? So if you're looking at this one, you're going to want to find if you're wanting to determine which one's going to be the most stable, you're going to look at the ones that's missing, or the one that's not missing as many electrons in its outermost shell. So in this case, neon, which is a noble gas and closely related to helium, as well as other elements in the noble gases, are going to be the most stable. Their outer energy shells are completely filled to capacity, and thus these atoms don't usually react with most things. So the atoms that don't have their outer energy shell filled to capacity bond to other elements to capacity bond with other elements to reach a stable state. So the number of bonds an atom can form is determined by the number of vacancies in the outer shell. So for instance, this carbon atom has 4 vacancies in its outer shell. So it can actually form 4 different relationships. So here you can actually see it bonding with 4 different hydrogen atoms to become methane, or CH4. So here's you can actually see those specific bonds that I was talking about, where the 1 electron from hydrogen is bonding at each one of those sites. So ultimately, this results in that methane molecule. And notice how the outer shells of these atoms are overlapping, and it creates this very solid electron cloud that's going to basically make all of these atoms happy and stay together. These are what you call covalent bonds, and it's when you're sharing these electrons. So when an atom shares the electrons, as this methane molecule is showing, that's where you're getting these covalent bonds. This is one of 3 different types of bonds that includes that are all chemical bonds, where atoms share electrons. This is probably the most common, and it's covalent. And there's a couple others that we're going to talk about in a second. So before we can get to those, we need to talk about electronegativity, which measures the atom's ability to attract electrons. So for instance, atoms with low electronegativity attract electrons, whereas atoms with high electronegativity attract electrons strongly. So for instance, sodium, which is Na on the far left there, and is on the far left-hand side of the periodic table, is going to be much less likely to pull an electron away from something like oxygen or chlorine. And so here you can actually see that electronegativity depends on the number of electrons to fill the valence shell, or the distance to the nucleus. So you can look at 2 things: the rows, which are the number of energy shells. So the more energy shells, the further away from the nucleus, the weaker the attraction to the nucleus. And then you get the columns, which are the increasing number of electrons. So the more electrons in the outer energy shell, the higher the electronegativity. So something like lithium, which has an atomic number of 3, it is on the second row there, has 2 energy shells. The lower one is filled, and the outer one has 1 electron. And it's most stable if lithium gives up one of its electrons to a secondary energy shell from something like fluoride, which is also on that second level, and it has an atomic number of 9, which means it has 9 electrons. So it has 2 on the first level and 7 on the second level, and that 7 needs another one to form that solid 8 to feel comfortable. Hopefully that makes sense. So this is that electronegativity differences can determine chemical bonds. So these are what we call ionic bonds. So remember that methane, which was composed of carbon and hydrogen atoms, neither of these atoms pull the electrons much more strongly than the other, and that's why we call it a covalent bond, because they're kind of equally sharing those electrons, which is not necessarily the case with everything. So these atoms with similar electronegativity form what we call nonpolar covalent bonds. So in this case, looking back at that methane molecule, you have 4 hydrogen atoms and 1 carbon atom, and they're all being held together by these nonpolar covalent bonds, and because neither the C or the H in this methane molecule have a partial positive or negative charge. And again, remember that some of these atoms have different electronegativities. So water is composed of hydrogen and oxygen. And if you look back at that scale of electronegativity, hydrogen is going to be much farther away than oxygen. So what happens is the hydrogens kind of have their own slightly positive molecule, whereas the oxygen atom is slightly negative. And so they pull together. And so one hydrogen occupies one of the spaces on the oxygen atom, and the other one occupies the other electron space. And so you get the H2O molecule that we're most commonly associating with water. So atoms with different electronegativities form different polar covalent bonds. So in this case, that water molecule that we're talking about, you have 1 oxygen atom with 2 hydrogen atoms that form this strong water molecule. And the water is held together by polar covalent bonds. And then you get to those very negative atoms that can take electrons. So in this case, it's actually forming an ion. It's not actually like still sharing those electrons anymore. So in this case, a chlorine atom is much, much, much better at attracting electrons than it is that it's able to completely pull an electron away from the sodium ion. And so basically what happens is a sodium ultimately becomes a positive ion and chlorine ultimately becomes a negative ion, and they're able to kind of merge together because they're pulling each other apart. These are called ionic bonds. And remember, again, back to the fact that ions are charged atoms, so ionic ions, it should be pretty straightforward. And that chlorine ion has one extra electron. So that Na plus ion has one less electron, they can merge together. Again, finally, it's what's creating that ionic bond. Now, sodium and chloride, which are both very, very noxious and dangerous chemicals on their own, especially in their pure states, where sodium is combustible when it's exposed to water, and chlorine is most famous for being chlorine gas, which was used in World War I and World War II, and is really, really nasty stuff. It absolutely will destroy your body. When you put those two things together, which are both incredibly harmful, they become sodium chloride, table salt. So the same thing that you're sprinkling on, your food every night, if you were to break those elements apart, you'd have some really, really nasty stuff. So it's kind of interesting to think about how, things that by themselves can be incredibly dangerous can come together and form some really cool stuff. So remember that some atoms are partially charged. And that kind of comes back to that polar covalent we were talking about. Since electrons spend more time near oxygen, the oxygen atom has a slightly negative charge. And since the electrons spend less time near the hydrogen atom, the hydrogens have a slightly positive charge. So if you think about the water molecule itself, it is slightly polar, which means it has one side of it that's a little bit more positive, the other side of it's a little bit more negative. And that's why water in particular has kind of the properties that it does. It's a very, very unique molecule because of these polar properties that it has. And partial charges in the molecules create hydrogen bonds. So these are the slight positive charges on the hydrogen atoms for one of the water molecules attracts to the slightly negative charge on the oxygen atom of a neighboring water molecule. And these are your ultimately forming your hydrogen bonds. And that's what's going to give water its really, really unique properties, where it can be this really cool liquid, it can also be a really cool solid, and, ultimately end up in a gaseous state pretty easily. And it allows it to kind of stick together in some instances. I don't know if y'all have ever overfilled a water cup just a little bit too much, and you get that nice bubble that kind of forms before the water dumps everywhere. That's where you're seeing those hydrogen bonds holding all those water molecules together. So kind of neat. Remember too that hydrogen bonds give water its emergent properties. So remember how we talked about emergent properties in the last lecture where, these things by themselves aren't nearly as special as when you put it all together. So that all that kind of stuff can be really important. So kind of neat. And specifically, they give water a collection of unique properties, and they're very, very important in protein and DNA structure. So without water having its very specific chemical properties, life as we know it would not exist. And that's why you hear about, people going out and exploring other places, particularly Mars or the moons of Jupiter, or whatever. And they're out there looking for water because life as we know it is primarily focused on existing around water. Now, there are some organisms on Earth even that are dependent on other, molecules of life, but they're very, 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 very uncommon and are usually found in very, very weird circumstances, like deep down in the hydrothermal vents in the bottom of the ocean or something like that. So without these emergent properties, the properties of how water gains by, being together, none of this would happen. All right. So let's do another little quick quiz question here. So nitrogen needs 3 electrons to fill its outer orbital shell, that last energy shell that we were talking about. So how many more bonds can an in atom make with other atoms? So remember again that a nitrogen atom has an atomic number of 7, an atomic mass of 14.0, which means it has 7 protons and roughly 7 neutrons, which means it also has, 7 electrons. And because of that, and we remember that, there's space for 2 electrons in the most closest band next to the nucleus. There's space for 8 electrons in that outermost band, which in this case, they're both on that second row, so they only have 2 bands. So in theory, there can be up to 10 in that outer row, or 10 electrons between the first 2 rows, but nitrogen only has 7. So how many bonds can nitrogen atoms make? I'll give you all about 5 minutes or 5 seconds or so. All right. So how many bonds can the nitrogen atom make? In this case, it can make 3. Now remember, we kind of talked through this a little bit, and I gave you a lot of hints at why this is the case. Now remember, there's a maximum number of 10 electrons that nitrogen can support because it's on that second row of the periodic table. And remember now that we know it can hold a maximum of 10, and its atomic number is 7, which means it has 7 protons and 7 electrons, we know that it can hold up to 3 more electrons, which means it's probably going to be a covalent bond of some sort. So let's try another question here. So based on the electronegativity chart below, which remember everything closest to the left is not super electronegative, whereas everything to the right is super electronegative, which bond should form between potassium, which is K, and chloride, which is Cl? Hint, the higher value indicates a higher electronegativity. The options are either A, a polar covalent, B, an ionic, C, a hydrogen, or D, a nonpolar covalent. I'll give you all about 10 seconds. All right, so let's see what the answer was. In this case, it's actually going to be an ionic bond, which is pretty straightforward because you've got something like potassium, which is way over here on the left, which has a very, very low electronegativity. And you have something like chloride over here on the right, which has an electronegativity of 3.16, which means that 1 electron is being taken away. The electron from potassium is being stolen away ultimately by chloride, which means they're forming that ionic bond that's going to make a really, really strong solid bond. And that's something to kind of important to mention, that the bond strength is different based off of the kind of bond. So for instance, a ionic bond is going to be the strongest bond, and it's going to be the one that requires the most energy to break. Then it goes to covalent bond. Then it goes to something like a hydrogen bond. So all those things can become really important when you're trying to decipher how everything breaks apart and all that kind of fun stuff. Alrighty. So there's some additional video tutorials out there that you can watch through here. There's also some cool videos that I found. They're not necessarily the most focused on college students per se, but there's some really good videos that explain, periodic table, atomic numbers, all that kind of fun stuff that's present in, what's the word? Your typical like AP prep courses that you might have taken in high school. It's very similar kind of stuff. I'll try to see if I can find some videos and post them onto web courses in a little bit to talk through some of those as well. With that being said, I think we're going to go ahead and wrap up lecture 3 here. I hope y'all are at least getting something out of these lectures. They're definitely pretty labor intensive on my end to produce, so please bear with me. They're not always going to be the prettiest, nicest looking things in the world, but I really am doing my best to try to make them as good as possible. If y'all have any questions, please don't forget to either reach out to me by email or by the discussion forums that are present on campus itself. Remember that primarily most of my office hours are by appointment only, and I will be hopefully trying to set up something here shortly that's going to be a way that we can all get a big group together and talk about this stuff over Zoom, which I'm still not super familiar with how to set up, especially for large groups. So bear with me. We'll be kind of learning as we go through some of this stuff. So just kind of hold out hope. With that being said, I hope you all enjoyed the first week. Please let me know if you're having any issues or concerns with this format of lectures or anything like that. And I'll do my best to rectify them as quickly as possible. And again, reminders, you have 2 quizzes that you need to do. One of them, which is just basically, are you a living being that exists? So that way you guys can get your financial aid, as well as another one that actually is much more important and is towards your grade. So please make sure you're doing those things. Otherwise, you're not going to get what you need. And with that being said, I hope y'all have a great afternoon, evening, morning, whenever y'all are watching this, and y'all are staying safe out there. Please remember, especially if you are taking in-person classes, to be filling out the thing on the UCF app, the self-checker, as well as make sure you're wearing your masks and all that kind of fun stuff. It is really, really important to make sure UCF can still have in-person classes. And while this class can't, I really hope that at least some of y'all are able to have at least one in-person class. So with that being said, I will see y'all real soon.